Welcome to the lecture. You may kindly recall that in the earlier lecture we had discussed about the test of hypothesis for the slope parameter under two types of condition, when sigma square is known and when sigma square is unknown. Now we are going to discuss about the confidence interval estimation for the slope parameter. Okay. So, first of all, the question arises, what is the confidence interval? If you say we had considered the model y is equal to beta naught plus beta 1 x plus epsilon, and we had estimated, for example, beta 1 has say here sxy upon sxx, and we had estimated beta naught as y bar minus beta 1 hat x bar, right. These are actually our point estimates. Point estimates means they are trying to estimate the value of the parameter at a particular point. Similar to this, we can also estimate these parameters in an interval. One of the use of the confidence interval estimation is that the interval estimates are given in the form of a lower and upper bound. For example, in the case of point estimate, suppose I estimate beta 1 say 2, then I would say that okay, beta 1 hat is equal to 2. But in the case of confidence interval estimation, we will estimate beta 1 is lying between 1 and 3 with certain probability, right. So, in the case of confidence interval, we try to create two bounds, Lx say and Ux. Lx is the lower bound and Ux is the upper bound, and our objective is to find out the Lx and Ux in such a way such that the probability that beta 1 lies between Lx and Ux, and these two bounds has to be found in such the way such that the probability of such an event is 1 minus alpha. Okay, so this Lx and Ux called as 100 1 minus alpha percent confidence interval, and 1 minus alpha is called as confidence coefficients. Confidence interval estimation and test of hypothesis, they are very closely related. There is a one-to-one correspondence between the two. So, many times when we are trying to deal with the software usually give us the confidence interval. So, by looking at the confidence interval, we can also infer about the outcome of a test of hypothesis. Right. Okay. So, first of all, let us try to construct the confidence interval for beta 1. Right. So, in the case of confidence interval estimation, 100 1 minus alpha percent confidence interval for beta 1 is found in such a way such that probability that Lx less than equal to beta 1 less than equal to Ux should be equal to 1 minus alpha, right. Now, in this case we will have two options. One option is sigma square is known, and another option is sigma square is unknown, right. We had seen earlier that when sigma square is known, then beta 1 hat minus beta 1 over square root of sigma square over Sxx. This follows a normal distribution with mean 0 and variance 1. So, what I can do here is the following, that I can write down, and this statistics is suppose here Z1. So, I would say here Z1 lies between minus Z alpha by 2 and plus Z alpha by 2, and the probability of such an event is 1 minus alpha, where your Z alpha by 2 are the alpha by 2 percent points on normal 0 1. It is something like this. For example, if I try to draw a curve, this is normal 0 1. So, if there are alpha by 2 percent point on the left tail, and if alpha by 2 points are on the right tail, and somewhere it is 0, and this region is 1 minus alpha, then the value of z on the x axis, here this is minus z alpha by 2 and here this is plus z alpha by 2. These values can be obtained from the tables, and these are standard values which are well known, depending on whether alpha is 1% or say 5% and so on. Right. Okay. So, now let us try to continue further, and we try to write down probability that minus z alpha by 2 is less than or equal to beta 1 hat minus beta 1 over square root of sigma square over Sxx less than z alpha by 2, and this is 1 minus alpha. Right. So, we try to solve it further, and we can obtain that beta 1 hat minus z alpha by 2 square root of sigma square over Sxx is less than or equal to beta 1. This is beta 1 hat plus z alpha by 2 square root of sigma square over Sxx is equal to 1 minus alpha. So, finally, I can write down that the 1 minus alpha percent confidence interval for beta 1 is the interval, that is beta 1 minus z alpha by 2 sigma square over Sxx to beta 1 hat plus z alpha by 2 sigma square over Sxx. Right. So, you can see here that this beta 1 can be obtained from the given data, and z alpha by 2 can be obtained from the table, and this can again sigma square is known, and Sxx can be obtained from data, and the same thing over here on the right hand side interval. Right. So, this is equivalent to something like we have obtained the Lx and Ux, which are a function of the sample values x1, x2, xn, and this interval can be obtained on the basis of given sample of data. So, this is our 101 minus alpha percent confidence interval. Right. Okay. Now, before giving the detail of its relation with the test of hypothesis, let us try to construct the confidence interval when sigma square is unknown. We have seen in the earlier case that when sigma square is unknown, then in that case the statistics beta 1 hat minus beta 1 over sigma square hat over Sxx, this follows a t distribution with n minus 2 degree of freedom, and let us call this as a statistic say T1. So, now based on this statistics on the similar lines, I can find out the confidence interval that the statistics T1 lies between minus T alpha by 2 n minus 2 and plus T alpha by 2 n minus 2, and the probability of such an event is 1 minus alpha. So, this is again equivalent to saying that if I have got a T distribution like this one, then this is here alpha by 2 percent point on the left hand tail, and these are your alpha 2 percent point on the right tail test, and the mid area is 1 minus alpha, and here somewhere it is 0, and corresponding to this thing the value on the x-axis of from the t table can be obtained as minus t alpha by 2 and minus 2 degrees of freedom, and this will be your t alpha by 2 and minus 2 degrees of freedom, and this is the probability density function of t distribution with n minus 2 degrees of freedom. Right. So, now let us try to further solve it, and we can write beta 1 hat minus beta 1 over, say here, sigma square hat over sxx and t alpha by 2 and minus 2 is equal to 1 minus alpha, or this can be written as beta 1 hat minus t alpha by 2 and minus 2 sigma square hat over sxx less than equal to beta 1 and beta 1 hat plus t alpha by 2 and minus 2 sigma hat square over sxx, and this probability is equal to 1 minus alpha, and here we are going to obtain the value of sigma square hat by sum of squares due to residuals divided by degrees of freedom, where the sum of square due to residuals are obtained based on the fitted model using the ordinary least square estimation or maximum likelihood estimation. Okay. So, now I have obtained the 101 minus alpha percent confidence interval for beta 1 when sigma square is unknown as interval like this. And beta 1 hat plus t alpha by 2 and minus 2 and sigma hat square over sxx. Right. So, here again you can see here that this value of beta 1, this can be obtained from the given set of data, and this sigma square hat, this can be obtained from the data, sxx can be obtained from the data, this t alpha by 2 n minus 2 is the alpha by 2% points on the t distribution, and its value can be obtained from the t table. So, this interval can be obtained on the basis of given set of data. Right. Now, before going further, let us try to understand that what is the relationship of this confidence interval estimation with test of hypothesis. So, let us try to discuss here relationship of confidence interval with test of hypothesis. Right. Okay. So, you have seen that in the case of confidence interval, what are we doing? Essentially, we are trying to find out here two statistics, Lx and Ux, the lower bound and upper bound, and we believe that this area is 1 minus alpha percent, and this area is alpha by 2%, and this area is alpha by 2%. Right. And similar to this thing, you can also recall that in the case of test of hypothesis, when we are considering the two-sided test of hypothesis, for example, if you try to recall the case of the Z statistics based on the normal 0 1, what we were trying to do, our critical region was lying on the left hand side and on right hand side, and this was alpha by 2, this was alpha by 2, and the mid area was 1 minus alpha with here something like this on the normal 0 1 curve, and this point was minus Z alpha by 2, and this point was plus Z alpha by 2 on the normal distribution. Right. So, now if I try to consider here the test of hypothesis that H1 beta 1 is equal to beta 1 naught. Right. So, the rule is very simple. If confidence interval, say this here Lx Ux does not contain beta 1 equal to beta 1 naught, then H naught is rejected. So, that is the relationship between test of hypothesis and confidence interval estimation. So, now what is the use of this thing? This is actually more useful in when we are trying to use the software. Sometimes the software do not give us the outcome about the test of hypothesis, rather they provide us the confidence interval in the form of lower limit and upper limit Lx and Ux. So, by looking at the confidence interval, we can again infer about the test of hypothesis, right. Okay. So, now after this we try to consider the test of hypothesis for interceptor. Term beta 0. You see, once you have understood that how we have constructed the test statistics in case of slope parameter beta 1, it is not difficult to create the test statistics for the intercept term beta 0, and all the testing procedure, everything that remains the same, exactly on the same line as we have done in the case of test of hypothesis for the slope parameter. So, just for the sake of understanding, I will try to quickly give you the results that we are interested now here in testing the null hypothesis for the intercept term beta 0 and is equal to beta naught naught, where beta naught naught is some known value, it is some given value, right. And we had considered the model, if you remember, beta 0 plus beta 1 xi plus epsilon I, and we had observed n sets of data. We had assumed that epsilon i's are IID following normal distribution with mean 0 and variance sigma square, and we had obtained the estimate of beta 0 hat as a y bar minus beta 1 hat x bar, where beta 1 hat was obtained as Sxy over Sxx, right. We had also demonstrated that expected value of beta 0 hat is beta 0, so it was an unbiased estimator, and variance of beta 0 hat was obtained as sigma square 1 over n plus x bar square over Sxx. Further, we had obtained the estimate of its variance, like by replacing sigma square by sigma square hat in the variance of beta naught hat, where sigma square hat is equal to sum of square due to residual divided by n minus 2, right. We can show that this beta 0 hat, this is a linear function of the normally distributed random variable y's. So, this also follows a normal distribution with mean beta 0 and variance sigma square 1 over n plus x bar square over Sxx. So, now using this result, we can construct the test of hypothesis under two cases, that when sigma square is known and when sigma square is unknown. So, first we try to consider the case when sigma square is known. So, in this case we can write beta 0 hat minus beta 0 0 divided by variance of beta hat naught, which is equal to sigma square 1 over n plus x bar square over Sxx, and this follows a normal 0 1 distribution when H naught is true, right. So, this is we call as Z statistics and denoted by Z naught, right. And similarly, when sigma square is unknown, then exactly on the similar lines I can develop a statistics beta 0 hat minus beta 0 0 divided by sigma square hat 1 over n plus x bar square over Sxx, and this follows a T distribution with n minus 2 degrees of freedom when H naught is true. And let us try to denote this quantity as say T naught. Right, okay. And here we try to estimate the sigma square hat again by SS res divided by n minus 2. Right. Now, what about the decision rule? Decision rules remains the same. We will just try to write down briefly. Right. So, now depending on my alternative hypothesis, I will try to write down my here decision rule under two cases when sigma square is known and when sigma square is unknown. Right. Okay. So, first case I would say, suppose the alternative hypothesis is H1 beta naught greater than beta naught naught. In this case, the decision rule is to reject H naught when, in case of sigma square is known, the value of Z0 is greater than Z alpha, where Z alpha is the alpha percent point on the normal 0 1 on the right hand side, on the right tail of the normal 0 1 distribution. And in case if sigma square is unknown, then the decision rules to reject H naught when T0 is greater than T alpha n minus 2, where T alpha n minus 2 are the alpha percent point on the T distribution with n minus 2 degrees of freedom. Similarly, if my hypothesis, alternative hypothesis is H naught beta less than beta naught, then I would say again that the decision rule is to reject H naught whenever Z0 is less than minus Z alpha in case sigma square is known, and in case when sigma square is unknown, then T0 is less than minus T alpha n minus 2. On the other hand, if my H1 is beta naught is not equal to beta naught naught, then in that case I will say reject H naught when mod of Z naught is greater than Z alpha by 2. In case sigma square is known, and in case sigma square is unknown, then this is mod of T0 is greater than say T alpha by 2 n minus 2, where T alpha by 2 n minus 2 are the alpha by 2 percent points on the T distribution with n minus 2 degrees of freedom. Right. Okay. So, now after this we can also construct the confidence interval. Right, confidence interval for beta naught. Okay. So, this is again that's not difficult, and it goes exactly on the same lines as we have developed the confidence interval for the slope parameter beta naught. Right. I am going to use the same statistics what we have used in case of test of hypothesis, the statistics Z naught and T naught under the two cases when sigma square is known and when it is unknown. So, the first case when sigma square is known, then in that case I can write down that the confidence interval will be obtained in such a way such that Z0 lies between minus Z alpha by 2 and Z alpha by 2, and the probability of such an event is 1 minus alpha. Right. Now, if you try to substitute this Z0, which is beta hat naught minus beta 0 divided by sigma square 1 over n plus x bar square over Sxx. Right. So, this becomes minus Z alpha by 2 between and Z alpha by 2, and the probability of such an event is equal to 1 minus alpha. And if you try to solve it for say beta 0, then we get the 101 minus alpha percent confidence interval for beta naught as beta hat naught minus Z alpha by 2 sigma square 1 over n plus x bar square over Sxx and beta 0 hat plus z alpha by 2 sigma square 1 over n plus x bar square over Sxx. Right. And similarly, in the case when sigma square is unknown to us, right, we simply have to replace sigma square by sigma square hat, and in that case we can write that probability that T0 lies between minus T alpha by 2 n minus 2 and T alpha by 2 n minus 2, and the probability of such an event is 1 minus alpha. Now, this after substituting the value of T naught, which is beta naught minus beta naught over sigma square root of sigma square hat 1 upon n x bar square over Sxx T alpha by 2 n minus 2 is equal to 1 minus alpha, and we can obtain the 101 minus alpha % confidence interval for beta naught in like beta hat naught minus T alpha by 2 n minus 2 square root of sigma square hat 1 over n plus x bar square over Sxx to beta 0 hat plus T alpha by 2 n minus 2 sigma square hat 1 over n plus x bar square over Sxx. Right. So, now again you can see that this is the value that can be obtained from the data, this is the value that can be obtained from the data, and this is the value which is obtained from the tables of T probabilities, that is T table, and based on a given set of data this confidence interval can also be obtained. Now, we consider the test of hypothesis for sigma square, and we would like here to test the null hypothesis sigma square is equal to sigma naught square, where sigma naught square is some known value and it is specified. Right. And the alternative hypothesis in this case is going to be sigma square is not equal to sigma naught square. One question arises here, under what type of condition we are going to use this type of test of hypothesis. We have seen that we have constructed various test statistics for conducting different types of test of hypothesis under two types of condition. First condition is sigma square is assumed to be known, and second condition is sigma square is estimated from the given sample and it is unknown. So, in the first situation when we assume that sigma square is known, then the value of sigma square is obtained by the experimenter either from his past experience, from some similar kind of experiments conducted in the past, or from somewhere. So, before assuming that the value which he is going to use is correct or not, he would like to conduct the test of hypothesis about the value of sigma square, which he is going to assume to be known and then to use in the concerned test of hypothesis. So, in order to construct the test statistics in such a situation, we are going to use the result where we know that n minus 2 SS res upon sigma square follows a chi-square distribution with n minus 2 degrees of freedom. Right. So, in this case the test statistic is defined as say n minus 2 SS res upon sigma square, and this follows a chi-square distribution with n minus 2 degrees of freedom under H naught. So, let us try to denote this statistics as say here C naught, and in this case the decision rule is obtained using the chi-square distribution. So, we know that the chi-square distribution is not a symmetric distribution. So, this is our x-axis, this is y-axis, and somewhere here there is alpha by 2 region, critical region, and here on this side this is alpha by 2 critical region, and in between this is the 1 minus alpha region, which is here acceptance region. Right. And the critical values which are obtained from the tables of chi-square probability, they will be here like this: chi-square at alpha by 2 level of with n minus 2 degrees of freedom, and this value is going to be chi-square with 1 minus alpha by 2 n minus 2 degrees of freedom. So, we can see here that in this case we reject the null hypothesis H naught if C naught is less than chi-square alpha by 2 n minus 2, or C naught is greater than chi-square 1 minus alpha by 2 n minus 2. So, this will help us in testing the hypothesis about the sigma square. Now, we can also construct the confidence interval for sigma square. So, now we consider the confidence interval for sigma square. So, in order to construct the confidence interval for sigma square, we are going to use the result which we had discussed earlier, that sum of square due to residual divided by sigma square follows a chi-square distribution with n minus 2 degrees of freedom. So, using this result, I can find out the confidence interval in the following way, that SS res divided by sigma square, this is going to lie on the chi-square with alpha by 2 percent point and n minus 2 degrees of freedom with chi-square point 1 at 1 minus alpha by 2% and n minus 2 degrees of freedom, and the probability of such an event is 1 minus alpha. You have to just keep in mind that chi-square is not a symmetric distribution like normal distribution or T distribution. So, that is why this distribution may look like this, and in this case we say that this is our alpha by 2%, and this on this side this is alpha by 2%. So, if I say that this is our chi-square alpha by 2 with n minus 2 degrees of freedom, then this point becomes chi-square with 1 minus alpha by 2 n minus 2 degrees of freedom, and this mid part is 1 minus alpha, and this is the probability density function of chi-square with n minus 2 degrees of freedom. So, now if you try to solve it, this becomes simply here SS res divided by chi-square with 1 minus alpha by 2 n minus 2 less than or equal to sigma square SS res over chi-square with alpha by 2 and n minus 2 degrees of freedom, 1 minus is equal to 1 minus alpha. So, 1 minus alpha percent confidence interval for sigma square is now simply SS residual divided by chi-square 1 minus alpha by 2 n minus 2 degrees of freedom, and SS residual divided by chi-square alpha by 2 n minus 2. So, these two values, the values of chi-square, they can be obtained from the tables of probabilities of chi-square probability. Right. So, they are available. Sum of square due to residual can be obtained on the basis of given set of data. So, this 1 minus alpha percent confidence interval can be obtained on the basis of given set of data. So, now we have completed the test of hypothesis and confidence interval estimation for all the model parameters, namely beta 0, that is the intercept term, beta 1, which is the slope parameter, and sigma square. Once we have estimated all the parameters, equivalently we have done the modeling and we have obtained a statistical model. So, on the next turn I will try to take a simple example, and using a software I will try to analyze the data. My main objective will be that whatever we have done in the case of simple linear regression model, we will try to demonstrate how those values have been obtained from the software and how they can be interpreted for getting a statistical model. Till then, goodbye.